This is number 14 from the review problems. And a 2 kilogram wood block is launched up a wooden ramp that is inclined at 45 degrees. The coefficient of kinetic friction for wood on wood is UK is equal to 0.2. The block's initial speed is 10 meters per second. How far up the incline does the block travel before stopping? So we first have to write our givens and finds, draw a picture, and establish a coordinate system. Next, we'll draw a free body diagram and a motion diagram. We'll apply Newton's second law to find the acceleration, and then we'll find the distance the block travels up the incline before stopping. So let's start with our givens and finds. So we're given that the mass of the block is 2 kilograms. The theta is 45 degrees. Mu k is equal to 0.2, and V initial is equal to 10 meters per second. And find, we need to find how far, so x final, how far up it goes, and we also need to find the acceleration. So we're going to draw a picture. So we have a block, we're going to start here. We know our block is headed this way. Our coordinate system is going to be x is in the direction that the block goes up, so it's rotated, and this is my y direction. And my block will end up here somewhere, and we're not sure how far this is. So this is going to be my x equals 0, and this is going to be my x final. Okay, so free body diagram. I'm going to draw in my incline and just put my dot that represents the block. My normal force is perpendicular, and my force of gravity is down. I have the force of friction, so the block is moving up the hill, so therefore my force of friction is down, opposite. And now I'm just going to draw in my components, so just put the dots for my triangle here. And I know this is my FGY, this is my FGX. They're not vectors, they're just the components of the FG vector, of the gravitational vector. And this is my theta. So this theta, if I extend this down, is the same as this theta. And if you're not sure about that, what you can do is look at this theta and then extend the FG down, and you'll see that because this is a right angle, if I extend this down, I have a right angle here. This is 90 minus theta, and this is a right angle, so this has to be theta. So 90 minus theta here plus theta gives me 90. So now I've got my free body diagram, and my motion diagram is going to look like, just gonna add it over here. So if I'm heading up an incline, say that looks like this, I'm starting out with a given speed, and I know that the block is going to be slowing down because of friction and because it's heading up a hill. So I have a long arrow to begin. Let's try to make that parallel. My long arrow, and a shorter arrow, and a shorter arrow to like a stop. And so these are my V's. Say V1, V2, V3, they were different. And then my accelerations are opposite. Okay, so I finished B, so this is part B. This is part A. And part C is to apply Newton's second law. So what I'm going to do is I'm going to apply Newton's second law both in the x direction and in the y direction. So let's start with the x direction. So the sum of the forces in the x direction is equal to ma, and I'm looking for A. So looking at my free body diagram, I have two forces in the x direction. So I've got my force of friction, and I have this force here, which is pointing in the negative x direction. So I have a negative force of friction minus Fgx equals ma. So now I want to do my sum of the forces in the y direction. equals 0, and it's equals 0 here because I'm not moving, my object is not moving away from or perpendicular to the surface. It's staying right here, so it's not moving in the y direction. And so my forces in the y direction, I have the force of the normal in the positive y direction, and I have the component of the force of gravity in the negative y direction. So I'm going to have force of the normal minus Fgy is equal to 0. And so the force of the normal is equal to Fgy. And looking at Fgy, this is adjacent to theta, and so therefore I'm going to have mg cosine theta. And I need the force of the normal because I need to use it for the force of friction. So I'm going to plug in. So I know the force of friction is equal to u times the force of the normal. And I know Fg, the x component of Fg is mg. Looking here, this is sine theta equals ma. And I'm going to plug in for the force of the normal. So mu mg cosine theta minus mg sine theta is equal to ma. So now I can cancel out my m's. And a is equal to negative g, factoring out my g, mu cosine theta plus sine theta. So I factored out my negative as well. So plugging in, a is equal to negative 9.8 meters per second squared times 0.2 cosine of 45 degrees plus sine of 45 degrees. So a is equal to a negative 8.32 meters per second squared. Now the next part, so this was part C, D, is determine the distance that the block travels up the incline before stopping. So I'm going to use the kinematic equation for velocity. So I'm going to use v final squared is equal to v initial squared plus 2 times AD. Now I know my A is in the negative directions, and I also know that my final velocity is equal to 0. So so now I'm looking for D, or let's call this instead of D, delta x, because this is my x direction, and so I'm trying to find this delta x along here. So so delta x is equal to v initial squared over 2a, and that's equal to 10 meters per second squared over 2 times a negative 8.32. And I'm missing forgot my negative here, so I have a negative there. This is meters per second squared, and so I get delta x is equal to 6.01 meters. So that's how far up the incline it travels before it stops.